Chemical bonding 2. The essential idea here is that covalent compounds form by the sharing of electrons. And the nature of science is looking for trends and discrepancies. For example, compounds containing nonmetals have different properties than compounds that contain nonmetals and metals. Also, use theories to explain natural phenomena, such as when Lewis introduced a class of compounds which share electrons, and Pauling used the idea of electronegativity to explain unequal sharing of electrons. Here's some examples of covalent bonding. We have ammonia up here, and we have some gummy bears here. The gelatin within gummy bears has covalent bonding. We have DNA here. The bonds holding DNA together are covalent bonds. Water is covalently bonded. What else? We've got a protein, a globular protein by the looks of it, here. All the bonds within this are covalent bonds. We've got the covalent bonds in milk here, within the lactose molecule, for example. And here we've got some pollution of Hong Kong. And the molecules, the airborne molecules in pollution, contain covalent bonds. A covalent seems to be a square here. A covalent bond is the simultaneous electrostatic attraction between a pair of electrons and positively charged nuclei. I know why the square is there. It's to remind you to make your flashcards for definitions. Covalent bonds usually form between two nonmetals. In a covalent bond, electron pairs are shared in order to give each atom a stable octet of electrons. The formation of the fluorine bond in fluorine gas is a good example. We've got two fluorine atoms, here and here, with 7 valence electrons. They move to each other. You can see this electron here is then utilized by this atom here to complete its octet. And now we have 1, 2, 3, 4, 5, 6, 7, 8 electrons in this fluorine. Hooray! A single covalent bond involves the sharing of one pair of electrons. The formation of oxygen-oxygen bond in oxygen gas forms a double bond. Oxygen has 1, 2, 3, 4, 5, 6 electrons in its valence shell. When two oxygen atoms come close together, they share 4 electrons. 2 electrons make one bond, another pair of electrons make the other bond. Let's count them up. 1, 2, 3, 4, 5, 6, 7, 8. So it has a full octet. Hooray again. A double covalent bond involves the sharing of 2 pairs of electrons. And you can probably guess what's coming next. The formation of triple bonds using nitrogen as an example. Nitrogen gas is a nitrogen bonded to a nitrogen. Nitrogen has 1, 2, 3, 4, 5 valence electrons. When they come together, when 2 nitrogen atoms come together, they share 6 electrons. So that's 1, 2, 3 bonds, as there's 2 electrons in each bond. Now let's just count if that's right. 1, 2, 3, 4, 5, 6, 7, 8. It absolutely is. So this atom has a full octet. Let's just check this one. 1, 2, 3, 4, 5, 6, 7, 8. This also has a full octet. So a triple covalent bond involves the sharing of 3 pairs of electrons. Now let's compare single, double and triple covalent bonds. You can see the single here, the double and the triple. You can see the bond length increasing from 0.154 bond length decreasing, what we're talking about. Bond length decreasing from 0.154 to 0.134 to 0.120 as you go from single to triple bonds. And the bond enthalpy increases from 347 to 612 in a double bond, 838 in a triple bond. The bond enthalpy is the energy required to break 1 mole of a given type of bond. The stronger the bond, the more energy is needed to break it. Therefore, bond strength is increasing as you go from single to triple bonds. Covalent bonds involve the sharing electrons. Covalent share because they care. And you can see this young lady sharing her ice cream with the dog. But don't be fooled. This young lady is probably going to take far more ice cream than the dog. She's evil. Electronegativity. Electronegativity will tell us about the sharing of electrons, how much each atom will share its electrons. It's a property of an atom relating to its ability to attract electrons. It's defined as the measure of the tendency of an atom to attract a shared pair of electrons to itself. Let's put a little square there, and you know what that means. It's measured using the Pauling scale. No or little tendency to attract electrons, 0. You have electronegativity rating of 0. If you have a very strong tendency to attract electrons, the maximum tendency would be 4. You can find electronegativity values in Table 8 of your data booklet. Let's look at the trends of electronegativity on the periodic table. So, metals have lower electronegativity than non-metals, which have a higher electronegativity. So, electronegativity increases as you go from left to right across a period. Elements higher in a group have higher electronegativity. Group 18 elements have no electronegativity. Let's look at fluorine. It has 4. This is the highest electronegativity. Bromine below it has 3. So you can see it dropping as it goes down the group. And you can see lithium on the left there has electronegativity of 1, far lower than fluorine. Potassium only has 0.8, far lower than bromine. There's 2 types of covalent bonds. The first is non-polar. Non-polar covalent bonds. These involve the equal sharing of electrons. A good example would be the hydrogen atoms. When they bond to form a hydrogen molecule, the electrons are attracted by each other's protons by an equal amount. So, here, the covalently bonded hydrogen molecule, here, you can see this electron cloud. You can see it's symmetrical. There's an even amount of electron density here as there is here. There's an equal probability of the electrons being found here as there are to them being found here. The other type, polar covalent bonds, involve unequal sharing of electrons. Now let's have a look. This means that the electrons shift more towards one atom. You can see here the hydrogen and the bromine and the cloud around it. There's more cloud around the bromine than there is the hydrogen. And you can see these little electrons here represented by crosses are nearer the bromine. Dipoles are regions of partial charge. And look at the symbols we use. We use delta plus for a region of partial positive charge and delta negative for a region of partial negative charge. The negative dipoles form around the atom with the higher electronegativity. So bromine will have the delta negative, and the positive dipoles form around the atom with the lower electronegativity. And there you can see again the delta negative is next to the bromine, so the negative dipole is next to the bromine, and the delta positive dipole is next to that hydrogen. This arrow represents the bond dipole, and the circle here I've drawn around this bit kind of reminds you that this end is positive because it looks like a plus, and it's pointing towards, the arrow points towards the negative dipole. Here you can see several arrows, and you can probably notice they're getting smaller, and with good reason. The strength of a polar covalent bond is related to the electronegativity difference of the atoms bonded together. What do we have? We've got hydrogen fluoride, hydrogen chloride, hydrogen bromide, and hydrogen iodide. We're going down group 17 here. You can see fluorine has an electronegativity value of 4, hydrogen 2.1. So the difference here is 1.9. The difference for hydrogen chloride will be 0.9. You have 2.1 on the hydrogen and 3 on the chlorine. 0.7 for hydrogen bromide and 0.4 for hydrogen iodide. So hydrogen fluoride has the most polar bond and hydrogen iodide has the least polar bond. There is actually a bonding continuum though. And you can see here we have values we use to separate the different sections. Below 0.3 we call bonds purely covalent. So if the difference in electronegativity is 0.3 or below, they're pure covalent. If they're between 0.3, if the difference in electronegativity of two atoms is between 0.3 and 1.7, then that's polar covalent. If the difference between two atoms is above 1.7, then ionic. Have a look at this. So below 0.3, pure covalent. Between 0.3 and 1.7, polar covalent. Above 1.7, ionic. Okay, use the electronegativity values in your data booklet to predict the type of bonds that form between these elements. Press pause and have a go. So, how did you do? Well done. You can do a dance of joy to celebrate your correct answers. And again, use electronegativity values to predict the type of bond in these molecules. Press pause and have a go. Well done. Interestingly, carbon dioxide, I'm just going to draw it, has an overall dipole moment of 0 because it's symmetrical. So the delta negative here and the delta negative here kind of are equally distant from the central delta positive. So it's not actually a polar molecule. You might be thinking that phosphorus trichloride is the same. You'll think, oh, I know, it probably looks like this. And so again, the dipoles would balance out. This is not the case because this is actually tetrahedral. Remember that kind of thing? That triangle means the chlorine is coming out. This dotted line means the chlorine is going away. And you can see all the chlorines here are below this phosphorus. So you're still going to get a dipole heading downwards towards this chlorine region from the delta positive phosphorus. The carbon-oxygen bond would of course be polar covalent, and the phosphorus-chlorine bond also be polar covalent. Can you attempt to fill this in, please? This shows the bonding in the period 3 oxides. Press pause and complete it. Okay. Did you get it right? Of course you did. You can see here that 1, 2, 3, the first 3 things that you think of as a metal, sodium, magnesium, aluminium, are all ionic. Then we've got silicon and phosphorus and sulfur oxides are all polar covalent. And then only the chlorine is bonding with oxygen purely covalently. These here are molecular covalent, and we have a giant covalent structure here with the silicon dioxide. Okay, we'll talk more about that later. Can you try and complete this, please? Press pause and fill it in. Okay, I know that you got it all correct because you are just great. So let's have a look. This time the sodium and magnesium are both ionic, but the aluminium trichloride is considered polar covalent, as is the silicon and the phosphorus chlorides. And then we've got sulfur and chlorine, obviously, will be purely covalent. I say obviously because both chlorine atoms will have the same electronegativity, and so the difference will be 0. Splendid.